Hello, multivariable calculus students. This is section 11.5 and it is on the chain rule. So what we're going to do is begin with this video and give an overview of the chain rule and some of the iterations to what you've seen in the past with the chain rule now that we have multiple variables. So from the past, remember that your definition of a chain rule can sort of be written in two different ways. The most common way is that if you have a composite function, let's say you have f of g of x, and you want to take the derivative of that. You take the derivative of the outer function and you leave the inside alone, and then you multiply by the derivative of the inside. And that's really the standard that we've used in the past. Another way to write this that might help us a little bit in what we're going to now study is that let's say you have some function where let's give it y is a function of x of t. So in other words, x is defined by t and y is defined by x, which really is the same type of idea of a composite function. But this time, when we think about the derivative, I'm going to use Leibniz notation to write it. So we have the derivative of y with respect to x, because remember y is a function of x, and then I'm going to multiply by the derivative of x with respect to t, and that gives me the derivative of x with respect to its input versus the derivative of y with respect to its input, and in total this simplifies to dy dt. So you're able to come up with this special notation, I guess you could say, for the chain rule, and that's really the one that we're going to focus on with regard to multivariable derivatives with the chain rule. So let's move on to the definition we have in our notes. This is considered case one, just because of the format of it. So what you have here is a function z, which is made up of x and y. So it has two inputs. We've been very used to that so far. However, each of these inputs, x and y, each are made up of a function of t. So there's sort of this layered approach. So you have a overall function z, which is made up of x's and y's. The x's and y's are made up of t's. So you have sort of two layers here. We're going to try to calculate the derivative of z with respect to t. So dz dt is what we're shooting for. And remember that z is made up of a function of x's and y's, and x and y is made up each of a function of t. And our formula is to take the partial derivative of the function, which is z, multiplied by the derivative of x with respect to t. Remember, that's connected directly to what I was mentioning above. So when you look at just this portion of it, it really has a lot of connection to what this type of Leibniz format says about the chain rule. And then you do the same thing, but with respect to y this time. So that's how we split this up. We kind of analyze each side of it based on our partial derivatives. So I'm going to go ahead and write down the formula here so that we have it, and then we'll work through the problem. So we're looking for dz dt, which is the partial derivative of z with respect to x multiplied by the derivative of x with respect to t, plus the partial with respect to y multiplied by the derivative of y with respect to t. A couple quick things on notation. Number one, notice that this is the partial derivative notation, and that's because z is made up of multiple variables. However, this is not the partial derivative notation because x and y are simply made up of one variable t. Okay? All right, let's take a look at the derivative of z with respect to x. So again, we're just focused on the partial derivative of z with respect to x, which is going to be 2xy plus 3y to the fourth. And then we're going to multiply by the derivative of x with respect to t. We're going to need the chain rule, so we're going to get 2 cosine of 2t. In a minute here, I'll highlight each of these parts so you can see the development of this. The next part is the derivative of z with respect to y. So we have x squared plus 12xy cubed. And then we're going to multiply by the derivative of y with respect to t, which is going to be negative sine of t. So let's take a minute just to make sure we're organized here. The derivative of z with respect to x is here. The derivative of x with respect to t is there. Derivative of z with respect to y is here. And the derivative of y with respect to t is there. So hopefully that helps sort of organize what's going on. All right, we're going to evaluate this when t is 0. However, if you notice in your equation, you have x's and y's as well. So we need to figure out what that tells us about x and what that tells us about y. So all we need to do is go up to x equal to sine 2t. And if t is 0, that means x would be equal to sine of 2 times 0, which is, of course, 0. And for y, we have cosine of t. So if t is 0, we end up getting a y value of 1. All right, so we have everything we need. We're just going to basically substitute everything into our equation for dz dt and figure out what we get. So we have 2 times x, which is 0, times y plus 3 times 1 to the 4th, and 2 times cosine of 0 plus 0 squared plus 12 times 0 times 1 to the 3rd. You can do the math on this one. We're going to get 0 for all of that stuff in the second half. This simplifies to, let's see, that's going to be, that's just going to be 3 times 2, and so we get a derivative of 6. Now, one quick side note here is that ultimately, I'm not going to show this just because it doesn't pertain very well to the next set that we're going to talk about. But technically, I could take sine of 2t and I could substitute that in for x. And I could take cosine of t and substitute that in for y. And I could make an equation of z that is of one variable t, and I could take the derivative of that. That is certainly possible, and that is completely acceptable. The reason that I'm not going to worry about it too much right now is that we're going to go on to the chain rule case 2, and that's going to complicate things a little bit. Okay, but keep in mind that we could actually take z, and instead of making z a function of x and y, we can make it a function of t only, and then take the derivative as we have in the past in single variable calculus. Okay, let's move on to the next page. All right, on the next page, we're going to look at a similar example just so you can see a second example of what we just did in the last problem. We have dz dt, and we're going to set up the formula really quickly. We have dz dx multiplied by dx dt, and dz dy multiplied by dy dt. So again, similar kind of thing. Z is made up of x's and y's, and then x and y, those are made up of t's. And we're just trying to calculate the derivative of this one. We're not going to evaluate it at any given point. So dz dt is equal to the derivative of z with respect to x, which will be negative sine of x plus 4y. And then we're going to multiply by the derivative of x with respect to t, which is going to be 20t cubed. And then we have dz dy, which is going to be negative sine of x plus 4y. Remember, you need to multiply that by 4 because of the chain rule. And then we multiply by the derivative of 1 over t, which is negative 1 over t squared. So I'll do the same thing here just because I know that we're still sort of learning what's going on here. Here are each of the derivatives. I'll highlight each one. And that's our format. Now I'm just going to rewrite it. You wouldn't necessarily need to. We're just trying to come up with the general equation for dz dt. But you might see it as negative 20t cubed sine of x plus 4y. Let's see, that's going to be a positive 4 sine of x plus 4y divided by t squared. So you might see it simplified sort of like that. But either way, we're just evaluating the general derivative there. Okay, let's go ahead and move on to case number 2. And you could maybe even expect this, I'm not really sure, but the second case here has the same setup initially. Z is made up of a function of x and y. However, x now is made up of a function of s and t, and y is made up of a function of s and t. And so all of a sudden we've become, we still have this like two-tier approach, but in both tiers you have multiple variables, which means that as you notice in the formula that you can see in our definition, all parts are partial derivatives because z is made up of x and y, and x is made up of s and t, and therefore when you're taking these derivatives, every single one of them is a partial derivative, unlike case 1 where x and y were made up of one variable. Now there is a little bit of a technique that our textbook and others suggest in terms of organization, and I think it can be certainly helpful. You can use it if you want, and you don't have to use it if you don't want. But here's what it looks like. It's basically a tree diagram. So think back to algebra when you did tree diagrams. If you have a function z that is made up of x and y, and you have a function x which is made up of s and t, and a function y which is made up of s and t, you can think of every path along this tree diagram as a partial derivative. So for example, this would be the partial derivative of z with respect to x. This would be the partial derivative of z with respect to y. The next layer would be the partial derivative of x with respect to s, partial derivative of x with respect to t, and then the partial derivative of y with respect to x, and partial of y with respect to t. So for example, let's say we'll compare it to our formula right here that I'm highlighting. So let's say you wanted to calculate the derivative of z with respect to s. Well, you would take your tree diagram and you would locate where you end up with s, basically, and you take each of the paths associated with, in this case, s, and think back to the tree diagram and probability. When you look at those paths, you'd be multiplying through. So in other words, we would multiply dz dx with dx ds. We can see that here. And then you would multiply dz dy with dy ds, which you can see there. And remember, with tree diagrams, you would add up the result of that. And so really, these formulas, you could, if you want more of a visual behind it, you could think of it as a tree diagram calculation. So if that's helpful, go for it. If not, then forget it and just try to go with the patterns. It's up to you. Okay, let's try example 3. So we're going to calculate both dz ds and dz dt. You can refer to the tree diagram that we just drew out. Here's our formula for the first one. So dz dx multiplied by dx ds plus dz dy multiplied by dy ds. So that's what I'm going to set up for my very first one. The derivative of z with respect to x would be e to the x sine of y, and the derivative with respect of x with respect to s would be t squared. Then the derivative of z with respect to y would be e to the x cosine of y, and we would then multiply by the derivative of y with respect to s, which is 2st. Let's go ahead and try to calculate the derivative of z with respect to t. And the formula for that would be really similar. So you have dz dx multiplied by dx dt this time, and then dz dy multiplied by dy dt. So this one gives us the same initial derivative, e to the x sine of y, but then we multiply by the derivative of x with respect to t, which is going to be 2st. Then we have the same thing here, e to the x cosine of y, but then we multiply by the derivative of y with respect to t, which is going to be s squared. So there's a quick example of that. You can sort of, I guess, predict what may happen next, which is that any level of this could add any level of variables. So in other words, z could be made up of x, y, and w, and x, y, and w could be made up of a, b, c or something. You could have all sorts of different levels of derivatives. In fact, when you're looking at your derivatives, x and y could be made up of separate variables. There's sort of this exponential application to what's going on here with regard to the number of variables and the level of variables. So in the next example, we'll take a look at one example sort of at the next level. All right, so what we have here is the general version of the chain rule, and basically what it states is that, like I just mentioned in the previous page, the original function could be made up of any sort of set of variables, and those variables could be made up of any set of variables, and so on and so forth. That pattern could continue. So we're just going to do one example. We won't go crazy with this necessarily, but we're going to look at the example of u, which is made up of x, y, and z, and then x, y, and z, which is made up of r, s, and t. So if we're trying to calculate du ds, let's go ahead and just, I'll show the tree diagram example of this. So u is made up of x, and then y, and then z. And x, y, and z are made up of r, s, and t. So I'm going to probably kind of run out of space here, but that's fine. Okay, we're concerned with du ds, which means that we want this set of three paths right here. So in other words, we have du ds equal to du dx multiplied by dx ds plus du dy multiplied by dy ds, and finally du dz multiplied by dz ds. So those are our parts to this particular derivative. So let's go ahead and calculate those. Change my colors. So we have du ds equal to, okay, du dx, so the derivative of u with respect to x would be 4x cubed y. The derivative of x with respect to s is r e to the t. Then we have the derivative of u with respect to y, which is going to be x to the fourth plus 2y z cubed. The derivative of y with respect to s will be 2r s e to the negative t. Then we have the derivative of u with respect to z, which is going to be 3u squared z squared times the derivative of z with respect to s, which is going to be r squared sine of t. All right, so it's really ugly. It's the key here is to keep organized. Now we're being told that we're evaluating this when r is equal to 2, s is equal to 1, and t is equal to 0. And so what we need to figure out is what is x, what is y, and what is z from that information. So we're going to go back up to the directions. If r is 2, s is 1, and t is 0, then x would be equal to 2. If we look at y, r is 2, s is 1, and t is 0, we happen to get the same thing, 2. And then for z, let's see, r is 2, s is 1, sine of 0 is 0, so z is 0. All right, now we will simply plug in all of that. So du ds will be, let's see, that's going to be 4 times 2 cubed, so 8 times 2 multiplied by 2 plus 2 to the fourth, so 16. Z is 0, so the rest of that cancels, and we would then multiply by 2 times 2, which is 4. The very last one here, z is 0, so that's going to cancel. All right, so let's simplify this down. So 4 times 8 is 32, times 2 is 64, times 2 is 128. 16 times 4 is 64, and we add those up and we get 192. Okay, so that is the basics of the chain rule. So what the next video will focus on is being able to do some of the implicit derivatives that that you've seen in the past and some of the connections to multivariable calculus. Thank you.